talk about our measures of center. Now, you guys, these are going to be the ones that you're the most familiar with. In fact, these are probably the first stat words that you guys learned back in like elementary school. You guys remember learning about mean, median, and mode. Learn about these all at the same time. They teach you all of these at the same time because these are all measures of center. When you're describing center, what we're trying to do is we're trying to describe the quote unquote what does a typical value look like? All of the numbers in my set are around blank. That's what we're trying to capture. All right, and all of those metrics, mean, median, and mode, do that kind of in different ways. So you guys know mean. I'm not going to go over this too much. This is just the average of the set. We'll talk about weighted mean another day. It's not really part of this unit, but I feel like you should know how to calculate weighted mean. Or you guys know the median of a set. This is your 50th percentile. The middle number in your ordered set, it divides your data into two equal halves. All right, and you guys know mode. Not something that we use a ton. Mode is your most frequently occurring value. I don't know if I spelled occurring right. I know all of those are measures of center. And depending on what I give you, you could use any of these, and all of them are appropriate if all they ask you to do is describe. So you could just pick one. If I gave you the raw list of numbers, whichever you want to find is fine. Now, in the real world, there are scenarios where sometimes one of these metrics is preferred over the others. All right, and that's if the data set that we're studying has extreme values in it. All right. And actually, when I kind of go into this, I think that you'll see why. So, like, let's imagine that I was like the mayor of a town, and I was looking at the economic health of the people that live in my town. So I was looking at income, right? Income per household, and then Bill Gates moves into my town. All right. Which of these metrics that we just talked about is going to change dramatically when Bill Gates moves into my town? You can just, yeah, your mean, right? Your average is going to get all messed up. Bill Gates is going to move in. He's going to pull that average dramatically up. All right. We say that element, that the fact that that happens to your average, we say that your mean is not resistant to extreme values. And actually, if you go into economics, or if you are the type that's really into politics and you look at these types of things, oftentimes when you see data reported on household income, they'll usually will report the median household income as opposed to the average household income for this reason. That average household income is usually not really representative of what is typical in an area, because typically the people that make the most money make a lot more money and changes the average in a noticeable way. All right, but that doesn't happen with the median. All right, the median, we say, is resistant to extreme values. Bill Gates moves in. The person that was in the middle, their income's not changing. So my median is going to either remain the exact same or will change very little. All right, so in data sets, we tend to prefer the median over the mean if we've got extreme values. Just for the sake of thoroughness, mode is resistant as well. It just is that usually in most data sets, you've got a wide variety of things that you could see, and so the mode is not typically the measure of center that we'll report. Although I am going to give you an example in 1 second of when we would use a version of mode to describe center. All right, so if I ask you to describe a set, first thing you want to talk about is a measure of center, and you can give me any of those three, and that's fine. And you only have to give me one, so you don't have to say, hey, the mean is this, the median is this, and the mode is this. That's just overkill. I don't need all those things. Just give me one measure of center to kind of sum up what a typical value is, okay? All right, let me give you some other scenarios of things that you might see, and just so that you can kind of be ready for if it occurs. So they may not give you the raw list of numbers to work with. They may just give you a graph, and you don't have to flip back to this page if you don't want to. You can just read it. But if I were to ask you to describe a set, sometimes they might just give you this graph, and so maybe they'll just give you a box plot, and they'll say, hey, can you describe this distribution? So you have to be willing to report any of the values and work with what they give you. I've taught this course for a long time, and I've taught ProbStat in the past, and I've got kids, it's usually in ProbStat, it's not so much in here, but I'll have kids that are in that class that are like, okay, I'm just going to talk about average every time. Like, that's going to be the measure of center I just talk about every time. All right, well, if I give you this box plot and I ask you to describe this set, you can't tell me the average because I don't know that information. I don't have enough information to figure out what the average is. All right, but the median I can find very easily. All right, so I would need to report the median if I was given a box plot. All right, so just be ready to report other things. The last scenario that you might see, and this one is a little bit more tricky for AP students, is if I were to just give you a histogram. And this will be a graph that we look at a lot, this type of graph. If I were to ask you to describe center here, I can't figure out the average based on this picture. Maybe at best I could estimate it, but I definitely don't know the exact number. Similarly, I don't know the median. I kind of know where about it's going to be, but I don't know the median either. And so I don't know mode. I don't have the list of numbers, so I don't really know mode. Well, kind of. What we're going to report when we have a graph like this, I'm going to show you the technical name and then what we'll usually call it. We're going to report what's called the modal class or the modal group. All right, but typically, this is the math name of this term. Typically, what we'll just refer to is where does the peak of this graph occur? That's another name for modal class. Modal class is just another way of saying mode. It's the class that occurs the most often as opposed to the value. All right, so in this case, this is the peak of my graph, is this tower right here. And so most of my individuals are in this 22 to 32 range. So if you said, hey, there's a peak in the 20 to 30, in the 20 to 30 range, that would be fine. That's you saying what a typical value is in this set. Does that make sense? All right, so while you're not necessarily reporting like the mode per se, you are giving a version of mode by reporting the peak. And so that will constitute describing center if this is all you're given. Questions on describing center of a data set? Going once, going twice. All right, then next page. All right, the next element of a set that we'll want to describe is the spread of that set. All right, this word here, variability, is the Oliver. Just when it. This is just at the end, so. Variability is a word that kids will tend to use spread, and when I'm talking to you, I usually will say the word spread. I'm going to try and make an effort to use this word variability more. Variability just is the mathier term that means spread. It means how much do the values vary from number to number? How different are they? And that's what spread is looking at. How spread apart are the values? All right. So why do we care about this? Well, if all I were to do, and this is what beginners do when they're describing a set, if all I were describing was center, then a lot can be lost. So you don't have to write this down. This is just me trying to go through an example. All right, let's imagine that I had two classrooms. All right, and these were the test scores in these two classrooms. If all I did was report center, and that's all I talked about, all right, if I were to look at classroom A, the average of that class is an 80, and the median of that class is an 80. All right, and then if I were to look at class B, the average of that class is an 80, and the median of that class is an 80. So if all I were to do was tell you those facts about the two classes, you would think, oh, these two classes are performing similarly. That's all you knew. All right, and obviously when I give you the numbers, you can see that that's not true. All right, what's different about these classes? In Class A, everybody is scoring the same score. In Class B, there's a wider variety of scores. That's what we're trying to sum up when we're describing the spread of a set. All right, and just like with center, how there's different metrics, different ways that we can measure spread. There's different ways that we can measure center. There's different ways that we can measure spread. I'm going to talk about standard deviation last because that's the most complicated one. I'll talk about the easy ones first. All right, so range. I believe that you guys are familiar with range. You probably learned it at the same time that you learned mean, median, and mode, I'm guessing. All right, range is just the distance between your maximum and your minimum. All right, I know that you know that. But I do want to give you a caution. All right, range is not complicated. I know that you guys can handle range. The problem is that occasionally kids will speak in a way that I know what you're saying, but is technically not correct. So, like if I were asking students to describe this set, a lot of times when kids are trying to talk about range, what they'll say incorrectly is they'll say, oh, this data set ranges from 22 to 61. And I know what you're trying to say. And if we were talking, that's a normal thing for you to say, and it's descriptive. Right? The problem is that this is a stat course, and the word range in this course is like a word that has meaning, and range is a metric that measures the distance between the biggest and the smallest thing. All right, so when you say it ranges from 22 to 61, they consider that you misusing the word range. So what you want to say is that the range of this set is 39, right, the actual distance between those things. Then if you wanted to give me the minimum and the maximum, like as an aside, that would be fine, all right? But just make sure that when you're reporting range that you're giving me a single value, all right? This is something that I've seen enough from smart kids. All right, kids in this class will very often just say it ranges from such and such to such and such. And that does not satisfy the spread component when you're describing. They don't take that. Other than that, range, easy to find. All right, interquartile range. All right, I don't think that you guys know what interquartile range is, but that's okay. It's easy enough. It's very much like range. Range is the distance between your biggest thing and your smallest thing. Interquartile range is the distance between your biggest quartile, your Q3, and your smaller quartile, your Q1. If you don't remember how to find Q3 and Q1, I'm going to go over that again later today. But when you make a box plot, it's part of the box plot that shows up. In fact, just to show you, if you do stat, calc, 1var stat, all right, this is what we did on the first day to get average and standard deviation. All right, if we scroll down to the bottom, you can see Q1 and Q3 down there as well. All right, so that's how you can get those values if you forget. All right. Last measure of spread that we need to talk about is standard deviation. And then I'll briefly talk about variance as well. Okay. I mentioned on the first day of class that standard deviation is a value that should have meaning to you. All right. What I mean by it should have meaning to you is when I say like, hey, the average of a set is 80, in your heads, most of you, if not all of you, are imagining like, oh, well, what that means is that the numbers in the set are around 80. Like some of the numbers are bigger than 80 and some of the numbers are smaller than 80, but they're all like kind of around 80. That's what average means when I tell you that the average of a set is 80. All right. When I say the standard deviation of a set is 5, all right, that should also like allow you to visualize something about the set. All right. And if it doesn't right now, that's okay. That's going to be what I show you. All right. I'll give you the word definition of what standard deviation is. I find in experience that word definitions in math are not audience friendly. I find that my teenage audience, they don't really love word definitions. They like to see it more, but I'll give you the word definition just in case that's how you learn. All right. Your standard deviation just stands for the typical, and that's going to be in quotes, the typical distance each value lies from the mean. All right, so if I say that the standard deviation of a set is 5, that means that typically my values are about 5 units away from the mean. To show you a more crystal example of what I mean by that, I've got an example down here that I think is going to illustrate pretty well what standard deviation is looking at. All right, so let's imagine that we've got 3 friends. They're going out and they're getting all-you-can-eat wings, and this is what they're putting down. Just, solid performances, nothing noteworthy, but, a good showing. All right, so we've got somebody at 827, somebody at 823, 29, and 21. All right, the average for the group is 25. All right, so again, in my head, I know, all the people in this group ate around 25 wings. All right, what standard deviation is trying to capture is how close were all of our individuals to that average? Were they really close to the 25 or were they kind of far away? So for each person, I would look at how far away was each person from the mean. So this first person was 2 wings off from the mean of 25. All right, this second person was also 2 wings off from the average. All right, this person at 829, they're 4 off from the average. All right, this person right here, they were also off by 4. All right, if I'm summarizing this set right here, this number is kind of what standard deviation is. Technically, what this number that we just found is called, and you don't need to know this, this is just, I don't want you to think that we just found the standard deviation. What we found is close. This is something called your average absolute deviation. All right, why I use average absolute deviation in my example is, students, this is very intuitive as to how I found this number. This makes sense where I got it. Standard deviation of the set is going to be really, really close to this. I think the standard deviation of this set is 3.1. All right. Why we use standard deviation as opposed to this is that standard deviation, the equation that we use to find it, is more usable in other branches of math. When we just did this just now, we used absolute value. I called this person off by 2. I didn't say this one was off by -2. I just said 2. So I just did the absolute values of how far each one of them were off. And absolute value, if you've taken a calculus class, is non-differentiable. You can't do calculus stuff with absolute values. And so that makes using this harder in other branches of math. So standard deviation does not use that. All right, and that's these equations up here. You don't need to know these equations, so if it makes you feel good, you can scratch all this out. All right, I don't need you to know them. Some teachers will make you calculate standard deviation once by hand. I don't know that that has a lot of, it really helps you understand anything better. So we're not going to spend the time. It's very tedious to do. All right, but saying that the standard deviation of a set is 3, what that means to me is all of my people were like more or less within 3 units of the mean. Some of my individuals were further than 3 away. Some of my individuals were closer than 3 to the mean. But everybody was like more or less 3 units away from the mean. Does that make sense? All right, so this is something that you can be asked to describe. Like I've seen questions where they say, hey, can you interpret this standard deviation for me? If they ask you to interpret something, that means like explain what this number means to you. All right, so that's just basically asking you to explain, that definition, or you can put it in your own words if you like. All right, that's the big takeaway with standard deviation. I will briefly talk about variance. All right, guys, don't stress variance too much. Here's what I really want you to know about variance. All right, first, know that variance and variability are different things. Variability is just a general term that just means like how spread out are things. All right, it doesn't reference something specific. Variance is an actual metric, like something that we can calculate. We can calculate the variance. All right. In terms of what variance is, here's what I need you to know about it. We talked about this actually on the very first day of class. Standard deviation, we've got 2 symbols, sigma and s. That's your standard deviation. What you need to know about variance is that your variance is just your standard deviation squared. So it's either sigma squared or s squared. Yes? Okay. Yes. So what, I know, very popular today, lots of things. So what you might be asked in terms of variance is I could see them, hey, they give you, hey, the standard deviation of the set is 4. What's the variance? So like, do I know like, oh, all I got to do is square it to get this? Or maybe they say, hey, the variance of this set is 36. What's the standard deviation? So just, oh, I can square root it to get to this. That's all you really need to know about variance for now. All right, in the short to midterm, we're not going to use variance really for anything. At the end of the year, variance is going to be useful to us for calculating certain things. And in other stat courses, variance has use. But like if you were to tell me, hey, the variance of this set is 125, like that doesn't help me visualize anything about the set. All right, so it's not really useful in a descriptive way. All right, so these are all measures of spread. Just like with measures of center, some of these are less useful and less informative if I've got extreme values in my set. In fact, you can probably tell me if Bill Gates moves into my town, which of these measures of spread is definitely going to get messed up and change a lot when Bill Gates moves in? Yeah, go ahead, say it again. Okay, you're right, that is going to change. I don't think that's the obvious one. What's the obvious one? Yeah, I think range is going to change dramatically, right? If Bill Gates moves in, all right, all of a sudden my maximum is going to get really, really big, all right, and so my range is going to get really, really wide. All right, range is not resistant to extreme values. And you already mentioned standard deviation. I don't think that this is intuitive. All right, but standard deviation is also not resistant to extreme values. All right, how you can maybe visualize and understand that it's not resistant, and I don't know if this is what you thought about, but it's measuring how far you are away from the mean. And we already discussed that your mean is going to change dramatically when Bill Gates moves in. So your mean is changing, and so everybody's distance away from the mean is going to change, all right, when Bill Gates moves in. All right, so because it's mean dependent, your standard deviation is going to change quite a bit, so it's not resistant. Which leaves us with interquartile range. Interquartile range is resistant. to extreme values. All right, and it's just like median. Why is it resistant? Well, Bill Gates moves in. My max is going to get really, really big. But the person that was in the 25th percentile and the person that was in the 75th percentile, their incomes aren't changing. Or like might change a little bit just depending on how many things are in your set. So my interquartile range is going to remain either the exact same or is going to shift just slightly. All right, so we would say that interquartile range is resistant to extreme value. All right, what do we think so far about our descriptions of center and description of spread? All right, we're going to take a break in 1 second. Let me just go over one last thing. And that is, again, just like before, I might ask you to describe something, but I give you limited information. So let's say all I give you is a box plot, and I ask you to describe this set. All right, a box plot, if they ask me to describe and I'm trying to look and assess spread, the strength of a box plot is that it shows spread really well. I can see two of my spread metrics like right away, right? My range is just the distance between my whiskers, so that's going to be easy enough. All right, and my IQR is just the distance from one end of the box to the other. This is my Q1 and my Q3. So finding spread given this graph is pretty easy. That's kind of the strength of this graph. All right. Histogram, while histogram is a preferred graph that we'll use quite a bit, not great for identifying range. All right, in fact, we're not going to be able to calculate any of our range metrics given a histogram. All right, I can't identify the standard deviation. I definitely can't calculate it. I don't know what the average is. There's no way I could calculate standard deviation given this graph. I could maybe roughly estimate where my Q1 and my Q3 are, but like I would just be guessing. So I can't really figure out IQR either. All right. The last thing is range, and that's going to be what we attempt to estimate, but we need to know that we can't find the range given this information. We don't know what the range is. All right. So what I'll usually do, just so that I can address the spread component if I'm given this graph, is I'll say that the range is roughly equal to or about equal to, and then what I'll do is I will subtract the minimum. Right? I know that 22 is my minimum. That's the starting value of my first class. So 22 is definitely the minimum. And then the highest possible value for the maximum. I don't know what my biggest number is in this tower. And actually, technically, 62 isn't in this group. 62 would technically be in the next group. But I'm just going to use the end point of my last class and the beginning point of my first class. And I'm just going to say that my range is, around 40-ish. And that's going to be fine. All right, they gave you limited information to work with, so they know that you can't know what the range is. And so if you're just attempting to estimate what the range is, this is fine. All right, now, before we take a break, let me just talk one more thing about this. I mentioned previously that how we're maths lawyers and we want to be very cautious how we talk. All right, if I were to say that the range is 40, that would be wrong. All right, and they would give you no credit for that component. All right, I don't know what the range is. In fact, I know actually that the range is not 40 because 62 is not in this group. All right, 62 would be in the next group. So I know that at most my range is 39 and some change. All right, or 39 if we're only talking one number. So to say the range is 40, all right, is an incorrect statement. It's definitely false. All right, but to say that the range is around 40, or if you said the range is between, and then you came up with a spread of values that the range could be, that would be fine. All right, so that's why I like to use this. Honestly, if they give you a histogram, a lot of times they will allow you to skip the spread component in the grading rubric, and they'll just say, hey, if they discuss spread, you don't have to evaluate it. But this is how I would attempt to address spread given a histogram, is I would just approximate it. All right. Okay. Let's take 5-ish minutes or so. If you need to run to the bathroom or get a drink, you can take the pass. I'll take attendance real quick, and then we'll come back and we will finish up the last couple of things. Okay, let's real quick. We'll talk about this last component, the shape of a distribution. This is one where if I give you the word definition of it, I don't think it's going to be very helpful to you. All right, it's looking at how values fall in a set relative to each other. I don't know if that seems like a kind of a word salad. So I think that the best way to learn about shapes is visually. Typically, how we're going to assess the shape of a distribution is we're going to look at a histogram. Histograms are, go ahead, you back. Histograms are, the strength of a histogram is it shows us shapes really well. All right, so I'm going to draw different types of histograms to illustrate all the types of shapes of distributions that we can see. All right, so the first shape that we could see is actually a family of shapes, is a symmetric distribution. The most common type of symmetric distribution is going to look kind of like this. All right. Yes, and we're actually going to talk about this later. Bell curves are symmetric, but not everything that has a hump in the middle are we going to describe as a bell curve. We'll talk about that later. All right, this is the most common type of symmetric distribution. We've got, it's symmetric for the reason that you'd think. We've got a peak in the middle. All right, and it's kind of even on both sides. It doesn't have to be perfect. So some kids asked me earlier, like, hey, what if like one of these towers on this side is slightly more than the other side? That's okay. All right, we're just trying to generalize the shape that we're seeing. All right, so saying something is roughly symmetric, approximately symmetric is perfect. Okay. Now there's other things that are technically symmetric. All right, so like this picture that I'm about to draw is technically symmetric. And this is symmetric as well. All right, the problem is that if you got either of these graphs and you described them as symmetric, while that is true, all right, they wouldn't give you credit for these, all right, because we have better names for both of these graphs. All right, the analogy that I make is if I were to show you this shape. All right, my son's learning shapes right now. I say, hey, which shape is this? If he said quadrilateral, all right, that's a wild answer for my 3-year-old to give. All right, and technically that's true. It is a quadrilateral. All right, but this is a very specific type of quadrilateral, is that we know it's square. All right, so like you want to give it the more specific name, and we've got more specific names for these second two graphs. So they are symmetric, but we have better names for them, and they would require the more specific name. In fact, this last graph that I just drew, all right, is the next one that I'm going to discuss. A uniform distribution is just all of my towers are about the same height. This is not a common distribution that we'll see. All right, but if I was looking at like how many students are in each of the 4 classes at Madison, 9th grade, 10th grade, 11th grade, 12th grade, that's probably going to be roughly uniform, more or less. But that's what we're looking at with a uniform distribution, not super common. All right, I'm going to go over skew left and skew right last. That's going to be the last type that I discussed because they're a little bit more complicated. All right, So down to number 5, bimodal. All right, bimodal means that I've got multiple peaks separated by a valley. All right, so we mentioned earlier today that your peak is called your modal class. That's the technical name of it. If you've got one peak, you are considered unimodal. All right, this is a symmetric graph that is unimodal. All right, if I can draw, like if you imagine you just kind of smooth out the graph, just like kind of just trace along the tops of those towers. If you have two hilltops separated by a valley, all right, we're going to call that bimodal. The two peaks don't necessarily have to be equal in height, so it's possible that you've got one peak and then maybe a second, slightly shorter peak further away from it. That's fine. All right, but we're looking for two distinct peaks separated by a valley. If you've got multiple peaks, now that's super rare. That's not something that you'll see naturally in most data sets. If you had like a third peak, you might say it's multimodal with 3 or more modes. All right, but really that's very rare. Bimodal is going to be what you see. So this graph right here, while it is symmetric, we would want to describe this graph as bimodal. Does that make sense? Just to clarify one potential mistake, this doesn't usually happen in here, but I had some students make this mistake the first time I taught it. All right, and I actually didn't really foresee this as being an issue, but it makes sense. They would look at this graph and they'd be like, "Oh, Mr. Grossman, this is bimodal. I've got two peaks, one right there and one right there." And I was like, "Oh, I never really thought about that." I see what you're seeing, but no, that's not bimodal. If you were to smooth this out, it's still just one peak. All right, this peak is 2 classes wide. It's a wider peak. All right, but it's still just one peak. All right, so you need to have this distinct valley in between for something to be considered bimodal. Questions on those first 3? All right. So the last graph type is unimodal. These last two, these skew left and skew right, are typically unimodal like this graph. But they feel backwards to kids at first. I remember learning this in high school, and I always felt like these were misnamed. All right, so skew right looks like this.
Oh, okay. Oh. I haven't gotten there yet. Oh.
All right, so that is a skew right distribution, and I'm going to explain why it's called skew right. So if you're sitting here thinking like, "Oh, I don't like this, I don't feel like it should be called skew right," you in high school, me, feel the same way. And I'm sure that my teacher explained why it's called skew right, and I was just goofing off and not paying attention. Yeah, but I remember like when I studied this just being like, it's the opposite of whatever makes sense. And that's a terrible way to learn anything. Just be like, hey, whatever your instinct is, the opposite of that. That's what it's called. All right, and that's silly. All right, and why I felt like this was wrong is like, why is this called skew right? All the stuff is on the left. The peak is on the left. The majority of my observations are on the left. Why is this called skew right? That feels backwards. All right, and so what I wasn't really thinking about is I was focused on the right part so much that I didn't think about this skew part. What does that word mean? All right, so what skew means is if we were trying to describe the center, or the typical value of this set, all right, the median of this set is going to be, I don't know, maybe like right around here. All right, now you don't need to know this, but how I just eyeballed and estimated the median is if you just like imagine that you had a can of paint and you wanted to paint half the picture, you want to like draw the line so that half of your paint would be on one side and half of your paint would be on the other. So you're kind of like estimating the area, and that's how you can kind of eyeball and get a feel of where the median is going to be. All right, so I'm guessing that my median is right around here. All right, now if I were to estimate where the average is for this set, all right, typically your median and your mean, you'd think that those two things are going to be close together. All right. But what happens in a skew-right distribution is you have this tail. And what's happening in that tail is you've got a few individuals. It's not many people, right? These towers are very short. All right, so it's not many people over there. But those individuals have values that are much larger than the majority of your observations. Income is distributed like this. All right, most people are making typical moderate amounts of money between maybe 60 and 100 grand a year. All right, but there's a couple individuals that are going to be making 300, 500, $1 million plus a year. Not many, all right, short towers, but those values in those towers are much bigger than everybody else. And so what's going to happen is your average is going to get pulled towards your tail. And so your average is going to be higher than your median, and this is why we call this distribution skew right, is that your average has been pulled to the right. Layla, question.
So do you kind of think better with like a box plot?
No, see it better. I don't know if you see it better. I mean, I think that you see it really well here, but you can see the presence of skew in a box plot, and I'm going to go over how to do that. But if you're imagining it that way, I think that you probably already know. Same idea with skew left. My median might be right here. I've got this tail on the left. It's going to pull my average down, and so my average is going to be noticeably lower than my median. Yes?
So, like, the bars represent how many people?
How often you see those values.
Okay.
And then left and right means, like, is it a big or a small number? All right. Grades tend to follow a skew left distribution, especially back in the day. You guys gotta chill. All right. Especially back in the day, I taught here for a while. It used to be when I first started teaching here, there was no floor for grades, so like you could get a 10% on a test. In my first year teaching here, I taught Algebra 1 was one of the topics that I taught, and you get a wide variety of skill sets in high school Algebra 1. And so like most of my grades would be kids getting A's, B's, and C's, right? But then you'd have somebody that's like, I asked them to factor, and they just write X on the page, and it's like, oh, bro, like, it's going to be a long year, all right? And they're getting a 9% on their math test, all right? That's going to be a skew left distribution. Those values are going to pull your average down noticeably. All right, and this fact, all right, where I can look at your median and your average is useful, all right, because especially from a test-taking perspective, because one of the common things that I've seen them ask on quizzes and tests that throws kids off is they'll ask you something like, hey, can you describe the shape of this set? And then they don't give you a graph, and they don't give you the numbers. All right, all they give you are summary values. So they tell you, like, the min is this, the max is this, Q1, Q3, they give you the median, they give you the average and the standard deviation, and that's all you have to work with. But you don't have a picture, and you can't make a graph. And so a lot of kids are like, yo, how am I supposed to know the shape of this? I want to, like, look at a graph. That's how I tell shape. Like, how am I supposed to know the shape of this distribution? Well, you can tell if your average and your median are pretty close to being the same, if they're pretty close to being equal, then that means my average hasn't gotten pulled up or pulled down by the tail of your distribution, which means that my distribution should be roughly symmetric. If my average is noticeably higher than my median, then that means my average has gotten pulled up. And that would be an indicator that my distribution is skew right. And if my average is less than my median, same idea. And that means my average has been pulled down and it's skew left. All right, so your tail is what's doing the skewing. All right, so it's where your tail is that decides if it's skew right or skew left. So my tail's on the right, it's skew right. Tail's on the left, skew left. Questions on shape? All right, so just to touch on something that Layla mentioned, that I talked about in my other classes. So typically, if you're shown a graph and asked to describe shape, a lot of graphs show shape really well. One of the graphs that students sometimes struggle to identify shape with is a box plot. There's multiple ways that you can go about thinking of this. I think that the easiest way for you to think about, hey, how to identify shape is just divide your shape in half and think of it in terms of left side, right side. All right, if my left side and my right side are looking more or less the same, then that's an indicator that my graph is roughly symmetric. What type of symmetric that is, that depends, but it's roughly symmetric if these two sides are the same. The other thing you can look at is just the whisker part. All right, are those whiskers roughly the same? And that's an indicator that it's roughly symmetric. In this case, my right side is much longer and my right whisker is much longer. That's an indicator that this distribution is skewed to the right, to that longer side. All right, so this is an indicator of a tail over here. All right, but for the most part, a lot of our graphs that you would be given show shape pretty well. So identifying shape, not so hard. Last thing, I think we're all done with shape. Any questions on shape? I think we're good. All right, last thing that we need to talk about today are unusual features. All right, so what types of things would constitute an unusual feature? All right, now, not every distribution is going to have these. So if I ask you to describe a set, all right, you should always talk about center, always talk about spread, always talk about shape. Those three things every single time. All right, unusual features, maybe, maybe not. I'm going to skip outliers for now. We're going to do that last. I'm going to talk about these two because they kind of sometimes come together. All right, so a gap is what it sounds like. Is if I've got a range of values with no observations in there, all right, that's a gap. I've got big values and I've got small values, but I don't have any intermediate value. Like, why is that happening? That's odd. So that might be something that's noteworthy. We call that a gap. If you're describing a gap, you would want to say where it occurs. You'd say, hey, there's a gap between this value and this value. You wouldn't want to just say there's a gap. All right. Relatedly, clusters are ranges of values where you see a lot of stuff. All right. Now, so like here and here, we would call those clusters. Now, clusters are a word that's sometimes used and sometimes not. All right, you'll typically use this phrase if you've got a graph like this where I've got two groups that are distinctly separated. All right, if there was no space here, then your graph would look kind of more like this. And typically you won't call these clusters. You would say I've got peaks here and here, and you just won't use that term. But the idea is kind of the same. All right, when you've got this gap in between, right, and you've got this group here and this group here, that can sometimes be an indicator that whatever you're studying has subgroups in it. All right, so like what I mean by that is, like, let's imagine that I went to my kid's daycare and we measured the height of everybody at this daycare. All right, well, what I would see is I've got a lot of short height for all of the toddlers and the little babies that are there. And then I've got a lot of tall heights for the adults that work there, and then I don't have any of these intermediate heights. All right, so if all I were to do is show you a graph and say, hey, these are the heights for the people in a building, you'd be like, yo, what is going on? Why is there only short heights and tall heights? Like, what kind of building is this that happens? Well, right, it's an indicator that, hey, maybe you've got subgroups, and you're going to have to kind of look deeper into, like, what's going on and why that's occurring. We've got a special type of building in this case that holds two very distinct groups of people. But those would be called clusters. All right. Last thing that we're going to talk about are outliers. All right, now you guys kind of know coming in, or you have a crude understanding of outliers. You guys understand outliers to be like it's a weird number. It's like it doesn't match with the other numbers. I don't like the look of that number. It's too different. And honestly, that's a fine definition. I'm not going to really add anything to that. That's gonna work. All right. The problem is that if that's all your definition is, and we don't really have like a standard for what's going to make something weird, then that can lead to some problems if we're trying to identify outliers in a set. So, like for example, if I gave you this set of ages and I said, "Hey, are there any outliers in this set?" What do you think? Is there any numbers that stand out to you in this set? 61. All right, a lot of kids will say 61 kind of stands out. I get it. All right, what if that person was 60 years old? What do you think? Still an outlier at 60 years old? All right, yeah, I'm getting some yes. Yeah, still an outlier. What if that person was 55? 55. Okay, so 55, no, but 60 was a yes. All right, so what about if they were 57 years old?
I think it's more than 10 away.
More. Okay, so at least you've got at least a number, but like you guys get where I'm going with this, right? Is that I'm just going to keep like kind of naming numbers, and everybody's got this invisible line in their head that they just kind of arbitrarily made up, right? And we can't all have our own set definition of what we're going to consider weird, especially if we're trying to be on the same page. So there is a definition of how we can determine outliers. There's actually a couple. I'm going to teach you the one that is most frequently referenced on the AP exam. It's also the one that your calculator uses to determine outliers. Now, I'm going to put a little star next to this box. I'm going to put the equation in here. And I was talking to the girls over here while we were taking our break. Typically, guys, on our quizzes and tests this year, you are going to get a formula sheet, all right? And you'll get one on the AP exam as well, all right? Unfortunately, this equation here is not on your formula sheet, so this is going to be one that you have to memorize. It's not a hard equation. It's pretty easy, but it's going to be one of the few equations where I'm like, yeah, you got to memorize this equation, all right? It's not on the formula sheet. All right, so for this equation, you only need 3 values. You need your Q1, you need your Q3, and you need your IQR. You need those 3 values in order to do these equations. And a reminder, IQR stands for interquartile range. We just learned that today. All right, so it's okay. I literally said it 30 minutes ago for the first time. You've never heard it before. All right, so finding these values, just as a reminder on how to do that, you can go stat, calc, stat, calc, 1var stat. That's going to give you, if you scroll down, that's going to give you your Q1 and your Q3. All right, the other place that you could go to get those values is you could make a box plot. So you could go into stat plot and make the box plot like we did the other day, and then a little zoom 9, and then hit trace. Then you can move your cursor around, and that will give you Q1 and Q3 as well. All right, so 2 places that you can go to find your quartile. All right, your interquartile range is just the distance between your quartiles. So it's just the distance between these 2 things. So my interquartile range is 17 units, 17 years. All right, and that is all of the things that I need to determine outliers. So now, to figure out if I have any outliers, I'm going to do 2 equations. All right, and just to preview how this equation is going to, or how these equations are going to work, essentially I'm going to calculate a lower bound, and I'm going to calculate an upper bound. Then I'm going to look at my list of numbers, and I'm going to say, are all of those numbers that I'm looking at in between those bounds? If all the numbers are in between those bounds, then none of those numbers are weird. All right. If any numbers fall outside of those bounds, then those numbers are weird, and we would call those values outliers. Does that make sense? All right. So how we calculate these bounds is we're going to look at our lower quartile, our Q1, and we're going to go 1.5 IQRs below that Q1. And then we're going to go to our upper quartile, our Q3. And we're going to go 1.5 IQRs above my Q3. All right, so just so that you can see this in action, 27 is my Q1 minus 1.5 times my IQR, which is 17. 1.5 times 17 is 25.5. So this is going to equal 1.5. So that's my lower bound. All right, my upper bound is 44 plus 1.5 times 17. And so this is going to be 69.5. All right, and so my minimum in my set, my age set is 22. That's my lowest value. 22 is in between those two bounds, so I don't have any low-end outliers. My maximum, my biggest number is 61, and 61 is also in between those two. So 61, also not weird, not an outlier. All right, that's how I would identify outliers by hand. Does anybody have questions on how I did that by hand? All right, now that you've seen it once by hand, I'm going to show you guys how to do it on your calculator. Most of the time, you'll have your calculator, so you won't have to do this most of the time. Occasionally, they're creative or they ask you, hey, is something an outlier? Show your work on how you decided. So knowing how to do this is occasionally something that you're asked. All right, but there is a graph on your calculator that is going to identify outliers for you visually. Just going to make them in so you can see them. So to make that graph, we're going to go into StatPlot, the same place I go to make all of my graphs. I'm going to hit enter on graph number 1. Make sure it's turned on. All right, now for the type, I mentioned this the other day. There's 2 types of box plots. All right, and I mentioned the other day that we're going to use this one with the little dots in the picture more often. This is why. This is what this graph is going to do. It's going to identify outliers for us. All right, any outliers that are present in my set, they're going to denote with little dots. All right, so I'm going to pick this box plot right here. The name of that graph is a modified box plot. That's all it's called. All right, so I'm going to pick this modified box plot. That's that guy right there, the box plot that has the little dots in the picture. And then your calculator is just asking, where is my data? It's in L1. Do I have a frequency list for this data? I don't have a frequency list. I'm just going to leave this blank. And then it's asking, hey, what do you want the dots to look like? Like, you get to pick your aesthetic preference for the dots. That's nice. All right, so pick whatever you like. And then Zoom 9 will make a graph show up. And this is unfortunately kind of anticlimactic because we're not seeing any dots. All right, but that's telling me that there's no outliers. And that's what we just decided using the equation. It was that there was no outliers in our set. Just so that you guys can see what an outlier is going to look like, I'm going to go back into that set. I'm going to go stat edit. And I'm going to go down to that maximum value of 61. And I'm going to change that 61 to 70. So now that value is big enough to be considered an outlier. And so now if I hit Zoom 9, you'll see I've got a box plot and I've got a little dot out there. So I can see I've got an outlier.
That's so cool.
All right.
Good morning.
Now, just little things about this graph. So just some common mistakes that I'll see kids make. I've seen questions where they give you this graph, and then they ask you something like maybe there's 3 or 4 questions about this graph, and one of the questions is, hey, can you calculate the range? All right. And you're used to minimum and maximum. All right, but this is still your maximum. All right, your maximum is your biggest value. So I can't just do right whisker minus left whisker. In fact, if you hit trace right now, you'll see when it names all of these points. All right, this is my minimum. Still, that's my Q1. That's my median. That's my Q3. Now, normally the end of my whisker is my max. All right, but my maximum is right here. This value doesn't have a name. It's, in this case, it's the second biggest number, and that's not, we don't have a name for that. So it just calls it X. All right, it's just like, hey, there's another X value of 49. That's this guy. If there was multiple outliers, it would call them all. If you would see them all, there would be multiple dots on here. All right, and then we got our max there at 70. All right, identifying outliers. What do we think? All right, I'm going to do one last thing with you, and then we'll call it a day. All right. I'm going to show you the question. Actually, we're going to do this on a separate page. All right. We're going to answer this question right here, but we're not going to answer in this spot. We're going to do it somewhere else where it's more convenient. All right. So this is a very common FRQ question. All right, and I was just talking, if you are going ahead and looking at the data journals, at this point now you'll be capable of doing the data journals if you wanted to. All right, if they ask you to describe a distribution, so it'll give you some, maybe it'll give you a graph, maybe it'll give you the raw data, it'll give you some background information, and it'll say part A, hey, can you describe this set? Or hey, make a graph, and then it'll say describe this set. All right, you need to read this and know what this is asking you to do. When they ask you to describe a distribution, that is asking you to talk about these elements. All right, it's not going to say, hey, do plus for this. That's not going to be what it says. It's just going to say describe, and that needs to prompt you to talk about all these things. All right, now they're asking me to describe the distribution for people with advanced degrees. That's in the box plot part of the note. So I'm just going to do this answer on this page next to this graph so that I don't have to flip back and forth. All right, so I'm just going to flip to this page. In fact, I'm also going to turn it sideways just so I can read it a little bit easier. And I'm just going to show you guys what a model answer is going to look like. All right, so if they ask me to describe this distribution, I need to know, I got to talk about these things. All right, so the first thing I need to talk about is center. All I have is this box plot, so I can't find the average. I do know what the median is, though. It's right here. And from eyeballing it, it looks like the median is around, 60, and that's $60,000. So I would say the median income for people with advanced degrees is around $60,000. All right, about, give or take. All right, center, done. All right, next, spread. This shows multiple metrics for spread pretty easy. I can find my range. I could also give IQR. Either would get you full credit for the spread component. All right, I'm going to choose to describe the range. Why I'm choosing that is because the thing I'm noticing about this graph as opposed to the other ones is that there's a wider variety of values that you can make. There's wider variety of money. And so I kind of want to capture that, and range captures that better. So this minimum is, around 20. And this maximum, is maybe around 320. Maybe it's more than that. So the range of incomes is roughly $300,000. Now, if you wanted to say this, it's from 20 to 320K. That's fine. All right, but if all you said was the range of incomes is 20 to 320, that would not be fine. Does that make sense? All right, so the range of incomes is 300K. Done. Spread done. All right, and then the shape of this distribution, again, Box plots, not ideal for seeing shape, but if I were to, this one is fairly clear. My left side much shorter than my right side, a very long tail on my right-hand side, indicating I've got a skew in that direction. So the shape of the distribution for income is skew right. Where the tail is. The tail is doing the skewing.
What?
All right. So, honestly, I think that would probably be a pretty good description in terms of unusual features. I can't see gaps in this graph. All right. I can't really see clusters either, so I can't really comment on either of those. As for outliers, all right, here's what I'm going to say. I want everybody to pay attention to this. And again, this is going to be my second comment on being lawyers. All right. If they want you to talk about outliers, they're probably going to give you a graph where it's obvious that there's outliers because they give you like a modified box plot and they mark them with little dots so that you can see, oh, there's an outlier, I'm seeing it. Or maybe there's a part A where they ask you to calculate, are there any outliers? So like you actually had to physically do the calculation, right? If they're not doing that, they didn't outwardly show you the outliers in the graph or explicitly ask you to calculate outliers, they probably don't need you to talk about them, all right? And why I bring this up is that kids want to be thorough, and they're like, oh, man, I feel like I should talk about this view, and then, like, is this an outlier? All right. If you don't know if something's an outlier, don't call it an outlier, because they're going to grade the wrongest thing you said. Right, like in this set, if you're like, oh, there's an outlier here at this whatever this maximum value is, and if that's not an outlier, you're wrong. All right. What I would say, if you're like dying on the inside, and you're like, man, I really feel like this is an outlier, like I don't know how to check, but I really feel like it is. What I would say is I would use my lawyer speak, and I would say, hey, there's a potential outlier at 320. All right. Now. Well, in this case, we could calculate whether there's. I'm actually going to show you a visual trick on how to do that in a second. But like, let's say you didn't have the time for that, or maybe you had a different graph and it was a little bit harder for you to say. What I would say is you can say there's a potential outlier at this value, and that's okay to say. All right. I didn't say it was an outlier. All right. So you can't say I'm wrong. I didn't say, hey, this is an outlier. I said it's potentially one. All right. That's not necessarily untrue, and they can see why you would say that because this value is much bigger than the rest. So it's not unreasonable for you to be thinking, hey, this is potentially an outlier. So that's how I would phrase it if I thought maybe this value is an outlier, but I don't want to check. Last thing I'll show you today is just a trick for this. It'll also maybe help you guys remember the formula for outliers. I know concretely that this is an outlier. All right. How I know is that this distance from here to here. That's my IQR. All right. This is 50% of my IQR. If I were to go that, this distance right here is 1.5 times my IQR. All right. That's 1.5 IQRs of distance. If I go 1.5 IQRs above my Q3 and 1.5 IQRs below my Q1, these are my bounds for what constitutes an outlier. And so I know because this is so far past that, even though I just did like a crude eyeball way of doing it, this value is definitely going to be an outlier because it's way past, my little eyeball method that I just did here. All right. Like I might not do that here because it's going to be a little bit hard for me to read. And so like this guy, I don't know if I would feel comfortable making a guesstimate as to whether this is an outlier. But this one is so clearly beyond where I'm eyeballing that cutoff point to be that if you were to call that an outlier, you could feel confident in that. But I don't think that they would want you to do that. I think that center shape and spread would be all that's required on this rubric. All right, that's it. We're done. Quiz next class. We'll do some practice to start. A reminder that there are progress checks on AP Classroom so that you guys can see what questions look like. And at this point, you should be able to do the data journals more or less. There's only one or two small things that I want to talk about next time.
Oh, yeah.
Those are the customers.